We're going to use partial derivatives to find dy dx for our implicitly defined function here. And we're going to do that because it's a little bit easier and cleaner. In the past, we've done it using our traditional approach to implicit differentiation, but now that we have partial derivatives, we can actually do this in a much more efficient manner. So let's go ahead and get the formula for that down, which is dy dx is equal to minus the partial of f with respect to x, and the partial of f with respect to y then divides that. And in this case, this capital F of x, y, is the implicitly defined function up above when we set it equal to 0. So we find that then by saying, well, okay, I'll solve this really quickly and set it equal to 0 and make that 3x squared minus 2xy plus y squared plus 4x minus 6y minus 11. And again, that's just setting this equation here equal to 0 and calling that result our f of xy. So now we go through and just find the individual partials, and that's not terribly complicated. We want to take the opposite of this quotient. So the partial of all of this now with respect to x becomes our numerator. And that again comes pretty quickly. We have 6x minus 2y plus 4 for our numerator. And then again, we're going to divide that by the partial of that same function with respect to y. Again, going through that term by term, I have minus 2x plus 2y minus 6. And there you have it. There's our derivative, dy dx, using our partial derivatives. Again, much faster and more efficient than using our traditional implicit differentiation approach. So now let's try another one here. And in this case, you can see we've got x, y, and a z variable as well. So now we're talking about z being implicitly defined as a function of x and y. And so that means that we're ultimately talking about finding these partial derivatives now. And we'll do this again using this partial derivative approach as opposed to our more traditional way of computing implicit differentiation. So again, let's grab our formula, and for this one, I'll find the partial of z with respect to x, and the computation is found by taking the partial of f with respect to x and dividing it by the partial of f with respect to z. And again, we're going to find f. In this case, it's a function of x, y, and z by setting this thing equal to 0, and then ultimately that function that we result is what f of x, y, z is equal to. So that means that I have our capital f of x, y, and z being equal to x squared e to the y minus yz e to the x. Again, just setting this equal to 0 and then calling that result our function. So now it's just a matter of taking these partials, and we'll look at this function here. We'll take its partial with respect to x, divide it by the partial with respect to z, and then of course we hit that with an opposite. So let's start writing this out. Again, the partial derivatives here will not be terrible to compute, and it also looks like we don't have to deal with anything over here looking like some kind of product rule or quotient rule. So that's good news. So let's find the partial with respect to x. Again, term by term, we end up with 2x e to the y minus yz e to the x, the derivative of e to the x being itself with respect to x. And then we divide that by the partial of f with respect to z. The first term here doesn't have z, so its derivative is 0. And again, differentiating with respect to z here, we get minus y e to the x. And just to maybe clean this up a little bit, I've got a negative and a negative here that can cancel each other out. So I would just maybe take the time to rewrite this way. yz e to the x all over y e to the x. And I think that's just fine to leave it right there. So there you have the partial of z with respect to x. The calculation for the partial of z with respect to y would go similar. We just use the formula directly and apply it.